Hello, everyone. Sorry I'm not able to be with you today. These ACS meetings come up like they do, and they're scheduled at odd times, but I promise you this will be the only lecture that we do this way all year long. Maybe I shouldn't make that promise because you never know what could happen, but who knows? My basement flooded last year, and that took me out of class for one day, too. I don't want you to miss any bang for your buck for the tuition that you're paying here at UDM, and so I figure we'll do an online lecture today and basically just use it to fill in for the regular lecture that I would have given. I'll be back in my office tomorrow, Wednesday, September 11th, and we can catch up after then. Otherwise, taking some notes today after turning in your problem set and getting the handouts that will be passed out will be a good way to start Unit 2 of our course. Because in fact, that is exactly where we are in Unit 2 of our course, the concepts of isomerism, and we're going to be talking quite a bit about different kinds of isomers in the coming days. So please pay attention, pull out your notebook, and we're going to be ready to go. 5, 4, 3, 2, 1, now. So we're talking about the concepts of isomerism. These are molecules or structures in organic chemistry that are related through the same molecular formula, but different ... There's something that they have in common. Their molecular formula. That much is true. Remember, we use the abbreviation MF when we're talking about molecular formula. But these molecules also have different something else. And there's a few different things they can have that are different. The main thing is that they have to be related through the same molecular formula. You'll remember that whenever we see molecular formula being used when we're talking about the different levels of organic chemistry that exist, we're specifically talking about composition. Our 5 C's, convention, composition, constitution, configuration, and conformation, are the things that help keep all of these different concepts in isomerism straight. So these structures are related through the same molecular formula or composition, but different, and that's where the other 3 C's come in. Constitution, conformation, and configuration. Still getting used to the drawing pen, guys. I appreciate your patience as we go through all this. So we're really talking a lot about the end of this unit of material, part 2 of the course. We should be able to compare and contrast any 2 structures that we have and determine their isomeric relationship if there is any. And that's really a good way to look at everything we're going to talk about under the concepts of isomerism. We're really talking about primarily relationships. You have a relationship with your parents and your friends and your aunts and uncles, and you have a relationship with all sorts of different other people in your family and people you meet all the time. And molecules do too. Only the key instance of understanding their differences and similarities is understanding they must start with the same molecular formula. Otherwise, they're automatically a completely different molecule. Even if you end up with only 1 or 2 extra or less atoms, 1 or 2 extra or less functional groups, you are completely different than the structure you're looking for. And this is really important because one of the cornerstones of organic chemistry is a very, very simple relationship between structure, which we said we would start with in our course, and reactivity. I probably won't surprise you to learn that the bottom line on the whole relationship is that the structure of the molecule determines exactly how it reacts. And of course, that's paramount when we're talking about biochemistry and biology. So finding out these relationships is very, very important. Probably the easiest way to determine your relationship with anybody else on the planet, and of course we can think about these structures, molecular formulas kind of being like the genes you guys are studying with Professor Kagi, and that's what brings you into your relationships with other people biologically, is through a family tree. On the family tree of isomerism, basically we want to observe any relationships that these molecules can have. And the bottom line is, if we have two molecules that have different molecular formulas, automatically we categorize their relationship as not isomers. In general, around you, there's a lot of people you are not genetically related to, and if you want to call those people friends or acquaintances, that's fine. You can think about isomers having the same kind of relationship. If things have different molecular formulas, they're simply not isomers, and we don't view them in the same way. An example would be a molecule of cyclohexane and a molecule of pentane. You notice that we have a molecular formula over here of C6H12, and over here we have C5H12. The different number of carbons automatically makes it so that we have a completely different set of molecules here, and these are basically not isomers. The family tree has to start at some root, and the root is, if you were given any two structures with the same MF, where would we go from there? Let's pretend like we do have two structures with the same molecular formula, and we're trying to find out what kind of relationship these two structures are going to have. The first question we ask, if you follow your family tree sort of like a flow chart, think about following your family tree back to a common ancestor in this regard. The question we ask is, are these structures completely superimposable? When I say completely superimposable, I mean completely superimposable. We should be able to put them right on top of each other, whether we're using our model kit or on some sort of a piece of paper drawing, and see that they're the same. To use an example similar to the one we just did, I know it's kind of silly to think about it this way, but if we take a look at these two cyclohexanes, they both are C6H12. Given any two structures with the same molecular formula, these two are definitely the same molecular formula. Are they completely superimposable? When the answer is yes, we have a very, very specific term that we use to describe them, and almost always they're either called identical or, less commonly, but sometimes you see in the literature, homomers. Remember, the root of the word isomer is iso means same, and meros from Greek means parts. Here we have homomers, and that means same parts, as in these things are made of exactly the same parts. And since they're superimposable, we actually don't even really commonly call them isomers. They're called identical, or homomers in this case. To continue with where we started, if the answer ends up being no, we definitely are going deeper into the isomeric family tree. Once we know that something is an isomer of something else, we tend to ask another question. Let's find out what that question would be. The first level of isomerism has structures that differ by connectivity. So the next question we can ask is, do these two structures differ in connectivity? We've already seen a few examples of this in the structures that we've drawn. And if the answer is yes, then we know something. How about an example? Again, cyclohexane, C6H12. Here's a cyclopentane with an extra methyl functional group. That's supposed to be a CH3, please bear with me. It shouldn't take you too long to figure out that we also have C6H12 in this case. We count all the H's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have C6H12 here as well. They are not superimposable. We cannot put them on top of each other and see the same structure. So we'll say, yes, they differ in connectivity. And if you remember our definition from our very first day of class of connectivity, then you remember that the nickname we give this concept is constitution. These are constitutional isomers. And they are constitutional isomers because they differ in their connectivity. If the answer is no, we go deeper into the isomeric family tree into an area called stereoisomerism. We are not saying stereo in terms of something that would be like in your car or at home that plays really, really wonderful loud music. When we're talking about stereo, we're meaning the strict Greek interpretation of that word. And stereos, for those of you who know your ancient Greek, I know you're all champing at the bit to be able to answer this question. Stereos is a word that means solid. The reason stereo amplifiers, speakers, and sound systems got their nickname is because you felt like you were being hit by a wall of sound, a solid wall of sound. We have a different kind of solidity or shape difference that we're going to see further down the isomeric family tree from this point. So while you do, I'm guessing, see a shape difference here for constitutional isomers, it's that difference in connectivity that sets them apart from regular types of isomers. The next question we want to ask is another simple one. Suddenly it doesn't feel so simple after I've written out all those words, but the question is, can you make the two structures the same after a single bond rotation? And this is a very interesting and unique quality of single bonds versus their double and triple cousins. Single bonds as an EPD do have the ability to rotate. We do not see this ability with double and triple bonds, and that makes single bonds very, very unique and actually brings us to the next level of isomerism. For instance, if the answer to this question is no, then we're going to learn at a later date about our friends the configurational isomers. We'll learn about them at another time, and there actually is a deeper part of the isomeric family tree that we'll talk about after that. However, if the answer is yes, we are at a level of what we're going to be discussing today, conformational isomers, or sometimes as they're known, conformers. Conformational isomers are two molecules that after they have been found to be not superimposable and not differing in connectivity, that they have the same structure after a single bond rotation. And it's really, really important to understand the deeper and deeper that we get into the isomeric family tree, the more subtle the differences are. The difference between a molecule like cyclohexane and methyl cyclopentane should be very obvious to you because of your knowledge of three-dimensional structures, even if you haven't started using your model kit yet, which frankly you should have been using a lot by now. But when I show you two structures that look like this and say, are they isomers? I would appreciate you going back to the top of the family tree and saying, okay, both of these structures are C4H10, so they're definitely isomers of each other, but they're not superimposable. What's the difference we have here? There's no difference between these two structures here and here there's no difference in these two structures here and here with regard to connectivity. They're connected exactly the same. A methyl functional group is connected to a methylene functional group, which is connected to a methylene, which is connected to a methyl. A methyl, methylene, methylene, methyl. That's the way these two molecules are related. However, if I rotate along this center bond here in the middle, I can make this one on the right end up looking like the one on the left, and as a result of that, I can make these two structures the same after a single bond rotation. The relationship between these two structures is conformational. And this also brings up another really, really important point. Conformers are the only kind of isomer that can change without breaking a bond. To convert any other kind of isomer into another isomer, you're going to need some kind of reaction. This is not true for conformational isomers. They are off rotating on their single bonds constantly, usually controlled by the pressure and the temperature in the area. The other kinds of isomers, like constitutional and configurational, would need some kind of reaction to be able to convert them from one to the other. These two are in equilibrium all the time, and that's a key concept to remember. Conformers are always in equilibrium with each other. Very, very, very important to keep in mind. Just a quick review of everything we've learned with regard to constitutional isomers. One of the first things you notice when you start comparing things that are constitutional isomers is that obviously we're looking for differences in connectivity. Some examples we've already done. We can also compare to some others. Here we have two molecules, and I believe both of these are C6H10. So if we went to our isomeric family tree and said, do they have the same molecular formula? The answer would be yes. And are they superimposable? The answer would be no, therefore they are isomers, and they differ in the way they're connected. One's a ring and one's some sort of an acyclic creature there. We could take a look at comparing the same cyclohexene to a molecule like this. Here we have C6H10 as before. Here we have C6H12. These are not isomers. And it's important to keep that in mind using the family tree to be able to determine what the relationship of different molecules is. Of course, if I were to ask you, it is not a trick question, it's just a matter of logic. The relationship between these two structures, you would say they have the same molecular formula, they're completely superimposable, therefore we're going to call them identical or homomers in this case if we want to use the technical terms used in the literature.